Okay, so this is basically this either famous or possibly infamous equation, which is basically the equation that begins the derivation of the Navier, Stokes, and the Euler equation. So this guy, again, this part is essentially d by dt, mass times velocity part is what this thing's doing. And then this is basically the force part. So this is just using the mass times the acceleration equals the force. So all this thing really is. So the previous video basically worked on moving this d by dt inside of this equation, and it came up with this, which is basically derived using Leibniz and Gauss. So the next thing to do is to basically start looking at that side of the equation. So the question is now, what is this? And for Euler, it's a little bit simplified because it doesn't have all of the forces that Navier Stokes has. So force net for Euler basically equals an external force, which you call G, since it could be gravity, force, and in addition, there's the force of the pressure. So this is due to the pressure in the fluid. So the external force is fairly simple, and this is practically by definition the Fg, which can be dependent on space and time, basically equals rho times some scalar function that depends on space and time. For instance, this could be gravity, as far as there's basically a gravity multiplied by the density would give, and then multiplied by the volume would be the force of gravity. So this could be like mass times gravitational acceleration. If it was gravity, then this would just be the gravitational acceleration. And of course there would not be a space or time dependence probably, unless the planet's doing something very unusual. So, however, in general, this will be equivalent to a general external force that's simply a scalar function of space and time. And that's pretty much by definition. And the other force is the force of pressure. So, and this is a little more interesting. So this is the force pressure. It depends on space and time. So basically the idea, and it basically depends on the pressure field, which is itself dependent on space and time. And the question is how. So basically take a little box here. I'm going to basically draw this in the Cartesian coordinate system, so that means x is pointing forward, y to the side. So that looks might look a little strange. I don't know how to good job with the box. well, actually, this. So here was this little box. And then this box has a width or length or whatever of delta y. And on either side of the box there's a force due to pressure. So it's basically pressure pushing in on this side, and there's also pressure pushing in on that side. So basically the force of pressure pointed in the y direction is going to equal the pressure, and let's say this is y naught, at y plus delta y. So this is basically y plus delta y. So this is looking at this force on this side. And this force is going to have subtracted from it the pressure. Just at y naught. And overall, if this pressure at y naught was 0, then the force would be going in the negative direction, so there's an overall negative sign in front of this whole thing. So that is basically the net force due to pressure on this little element in the y direction. Oh, except there's one more component that's very important. There's the area component, and that's the area of this side right there. It's the area of that thing. So this is dA. So another way to write this is basically the pressure and this is just going to use basic calculus, so pressure dy y minus pressure y naught divided by delta y. This basically goes like the derivative of the pressure with regard to y. So we can substitute this into force equals, so this is basically this thing, however there's going to be a delta y out here, so this was divided by delta y and then multiplied by delta y, so this is derivative with respect to y, and divided and multiplied by delta y. Delta y and then delta area. And delta area goes like dx and dz, and delta y goes like dy. So what this ultimately looks like basically equals or goes kind of like partial derivative of pressure with respect to y times dy dx z, which of course is basically the volume element. So we basically take an element in space space. So this is a big element. And then basically look at this. Divide it into like a line in the y direction. Then for each of these little elements, this equation holds. So it turns out that if basically all of the elements are added up, what happens is this looks like the total force along the y direction is going to go like negative of the integral of the pressure over the y times the volume integrand all along this. And this basically it holds true for every single one of these stripes. The pressure in the y direction can be computed by this integral. So there's also of course equivalent integral. What happens is those equivalent integrals so there are also other integrals that basically look the same, but they're basically for the other components. So there's also integrals that look like f. So there's also the integrals that look like f of px equals negative with respect to dx, dv, and there's an integral that looks like so in the end, what this basically means is the force of the pressure as a vector actually equals the negative of the integral of this vector, which looks like dx p y and d rho p actually dc. And then times the integral of the volume. And this thing, of course, is the gradient of p. So what that ultimately shows is basically you have this equation, force pressure equals the gradient of negative grad p volume. And so for the individual, the force of P is basically by definition at this point equals to the negative gradient of the pressure. Since this is by definition basically the force per unit volume. And of course the pressure can depend on space and time. So what that ends up doing, putting this back together, the force net for the Euler equation equals this rho times g, which is the external force, as close as a vector field. And then on top of that, it's added to the force of pressure, which is actually going to be subtracted. So that's the negative gradient P dependent on space and time. Okay, so then the next idea is to basically go back and look at this thing. So I'm going to take this guy. So this was from the original equation. Okay. And so this thing now equals what has just been derived, basically. So this now equals over the volume around the kth particle. And this is rho, the external force, space and time, minus the gradient of the pressure. It depends on space and time. And then there's basically the volume term on the outside. So that basically finishes the first term. So the only thing to do is go back and basically grab the entire Euler equation, go back up here, and basically take this thing and combine this with the first term. And copy this. Because this thing is going to equal the first term, so I basically forgot how to paste. Okay. So you have finally this guy times, and this guy equals this, as can be seen back on top, because this was the left half of that equation. So this is this half, that is the right half. So this is the right half. So this thing equals the right hand side, which is this thing, which equals that thing. So this is an integral. I'll put this in. The external force on space and time minus the pressure, space and time, and then the volume. So this thing is actually the Euler equation in all its glory, except that there needs to be one small modification. This equation was actually written with for the component in x, and the right hand side is equal to the entire equation. So you can vote this to the entire equation, and that in fact is the Euler equation. The color I like, sure it is. So this guy is basically the Euler equation, which is basically just using force equals mass times acceleration and applying it to a fluid. That is basically all that was done to derive this, aside from various manipulations that that or just mathematical. So I'm going down and I'll go like this. So this guy, a little bigger, just label it. The rest of this video will probably be a complete waste of time. Okay, so this is the Euler equation. Oops, does not need to be. Euler. I think I spelled that correctly. Euler equation. Okay. So the next video will basically go over each component of this equation and go over what it actually implies in the sense of actual physics. That will be the subject of the next series of videos.